Tools and Technology Seminar Series. There's a sign-in sheet going around. Please try to sign in. We have a presentation next week, and then of course we're not going to have a presentation on Thanksgiving Day. I didn't really think anyone wanted to come in for that. And then we'll have startup again, of course, the week after Thanksgiving. So pleased to present today's speaker. We have Mitch Fernandez, who is a grad student in DCM&B in Keyvan Adarian's lab.
Hi. Thank you, Marcy. Thank you, everybody, for being here. My name is Mitch. I've been working for Keyvan for about a year and a half. Started on a project that I'll talk about briefly, kind of on hold for the moment. But I was going to give you an intro to TensorFlow. This is going to be pretty high level, so if you're a deep learning expert, you might be a little bored. So what is TensorFlow? Google put this out about a year and a half ago. It's a machine learning platform that they're using for a lot of things. It was originally geared for deep learning specifically, but you can do very basic things with it as well, even though it would be kind of overkill. It's currently available for pretty much every operating system. I think it was challenging to get it on Windows about a year ago. That's no longer true. It has a lot of good interfaces for it include Python, which is what it was geared for, but you can also do C++, R. I think there's a MATLAB interface that is kind of maybe not official. So whatever programming language you're used to, you can probably use TensorFlow with it. It's very fast. It's got a lot of really good tools and optimizers in it for deep learning, which is one of the main reasons for using it. So why would you use deep learning in the first place? Well, there's lots of applications, but the most common one, or the classic one, is object recognition. If you've got an image, you want a machine to figure out what's in it. And everybody loves seeing cats, and this is one of the things, I don't know if this was the first thing they tried to train machine vision with was cats, but apparently it's the most popular at this point, I think. What you want to do if you've got an image, you want to figure out what's in the image. You want a machine to be able to do it. One thing you can do is first identify what the object is, and this is your cat. Another thing is you've got multiple objects, you want to differentiate between them, so you've got cat, duck, dog, and you might want to actually find out the outlines of these images. This is going to be a value when we start talking about the medical imaging things. I don't have really great examples of medical imaging because, as far as TensorFlow, because I don't know anybody who's actually doing that. We're not actually doing it in our lab. We're going to be doing it with my project, but like I said, that's a bit on hold for the moment. So my interest was in understanding how people learn how to move, especially when the moves are quite complicated. I've been practicing martial arts for a decade or so, and I'm really, really bad at it, but I learned it over time, and I was trying to figure out ways of getting people to learn it more easily. And I started thinking of the medical applications for this. I started realizing that if you could get a machine to visualize a person as they move, you could classify their structure in a way that's very similar to any other simple structure like numbers or things like this. If you can get an outline of what that person is, how that person is standing, and how that person moves, you might be able to identify problems with how they're moving and figuring out ways of getting them to move a little bit more efficiently, a little more fluidly. Again, this is a martial arts, and you can see that these drawings are kind of ideal, and this is an expert in a position, and there are little differences here between how he's standing and how that position might be. And of course, he's standing in a particular pose that isn't demonstrated here, but if you look at the feet, there are differences. How do you get the computer to spot those differences and figure them out? And are they predictive of what this person is going to be doing next? Of course, what I was going to be doing was not just static images, I was going to be using video. We ran into problems with vendors, with augmented reality systems. We had a nice setup, but we were realizing this is going to take years to get done, and I'm a grad student. I would like to get out of here at some point. But the medical application was for rehabilitation. People who had suffered strokes, if we can figure out the whole idea of how they're learning, we can come up with ways of having them try to perform a motion and having them see what they're doing and how to adjust it. So this was our application. I'm hoping to get back to it at some point, but for right now, let me get on to how TensorFlow itself works. So what's a tensor? This is a problem that, a question that people ask that surprises me quite a bit. Tensor is just a matrix, maybe of 0 or more dimensions. So a zero rank tensor would be just a scalar, then a vector would be a rank 1, and as you add dimensions, a matrix is just 2 by 2. You can have you can have 3 dimensions, you can have 4 dimensions, you can have multiple dimensions, and TensorFlow is just a method for getting these matrices of different dimensions, running them through a calculation process of matrix multiplication, matrix manipulation, and coming up with an output for what you're doing. So in this basic example, which is actually taken from a TensorFlow structure, your nodes here are calculations, and your edges are actual tensors that are flowing through this flow graph is what they call it. And the flow graphs can get pretty complicated, and TensorFlow has a nice way of visualizing what you're doing. You can code it up and just use something called TensorBoard to visualize all sorts of things about how your graph is structured and how it's functioning. Now, an important detail here, when you're using TensorFlow, the first thing you have to do is actually construct your graph, even without any data, which means you have to assume that you're going to get data that's going to flow through it, and so you have to have placeholders for those things. And you just have to account for them when you're constructing your graph. So what happens when data is flowing? Well, you're going to have some kind of input. I'm going to talk about the classical example in a minute, where your inputs are going to be something you're trying to identify, something you're trying to classify. You're going to run it through some calculation or some series of calculations, and then you're going to get an output that will hopefully help you classify what it is that you were looking at and identify what was in your picture or whatever it is that you're trying to process. This is basically the very basic structure of any kind of neural network. Is you have some set of inputs, which are things that you're trying to classify. They're fully connected, which means each input is connected to every calculation node in what's called a hidden layer. It's called hidden layers because you won't necessarily know what the layer is doing, even though you kind of can backtrace it, but it gets complicated when you have a lot of layers. And this layer is just manipulating your input. These, again, are the tensors. Those are, again, manipulated out, and they end up coming up to an output, giving you a prediction of what it is that you input. So you don't know what you had. You had an image with something in it. You're trying to classify it. You do a series of manipulations here. From here, you have new outputs that go into some other layer. You do another series of manipulations, and then you come up with something that resembles a prediction of what it is that you had. And just to clarify this, as I was saying, these are all calculations, and these are going to be your outputs. These are just your tensors that are going from layer to layer till finally you get an output. So the classic example is handwriting recognition. If you saw that guy in the martial arts thing, standing like this, to me, he kind of looked like a letter or a number. You could see how you could reduce that to that. So this is why I like this example, and it's the one that everybody starts with. There's a database of characters 0 through 9 that people have handwritten. I think there are about 70,000 of these characters in the database. The idea is to get these characters, use them to train a network, and then predict which character you have. This is just an example of how the neural network would work. It's called MNIST. I don't remember what it stands for, but it's publicly available, and it's used all the time. So, for example, if you have the number 3 and you want to manipulate this as if it were not just a number but as some picture, you can break this down into a little graph of pixels that you're looking at, with each pixel having some kind of brightness or intensity. And based on that brightness or intensity, you can start learning what a 3 looks like, or what a 7 looks like, or whatever number you have. And again, what we're doing is we're starting out with this group, and we're creating an input layer. Since each number is in a little 28 by 28 graph, one thing we can do is, instead of representing it as a matrix, we can represent it as a vector and just break it into a vector of 784, of size 784. It just makes it a little bit easier to think about how this is happening. You do lose some information by converting a rank 2 tensor into a rank 1, but it's still good enough for this purposes. You pass You pass information from each one of these pixels into some hidden layer, which does some matrix manipulation, and then it goes to an output layer and gives a prediction of what number you have. Now, you actually know what's in this database. So you look at your input, you do your manipulations, and you get some result. And your result is going to be wrong. What you do then is you do something called back propagation, or some other way of figuring out why your number is wrong. And you basically just adjust some of these weights in your hidden layer and do the process again over and over and over again. So you're training this model to figure out what your 3s look like, what your 7s look like, etc. The code for doing this is actually quite simple, and I wasn't going to go through any code, but I decided this morning that I'd actually just put it in so you could see it's just a few lines to do this entire process. It's not complicated at all. So TensorFlow is really designed for people who don't want to, I don't want to say that for people who don't want to spend a whole lot of time coding, but it's pretty easy to pick up. So once you've passed all your numbers in through this process, you're going to come up with some kind of a mask that kind of tells you this is going to be your basic prediction. This is an example of what your mask would look like, and these are your weights. The redder it is, the more likely that this is the character that you're looking at. The bluer it is, the less likely that this belongs to the character you're looking at. So for each time you pass something through it, you use this mask on it, or the model will use this mask to determine, okay, this picture that I'm looking at fits this this character, or doesn't fit this character, and it comes with a prediction of this is a 2, or this is a 7, or whatever it is. As you're doing your training, the first time you do it, you're going to get everything wrong. As you continue to process everything through this model, you're going to get better and better and better. And with TensorFlow, you can visualize how it's improving each time you do it. And this is an example of that, of how your loss function is improving over the course of your training. And you'll see that it's actually pretty bad here, and it gets smaller and smaller and smaller until you end up having a pretty good result. All right. So this is these are some images that are taken from my lab. This is a paper that Nagar put out last year, and this is another paper that was done by somebody else. The idea here is we have people who've had traumatic brain injuries, and we're trying to identify areas of trauma. What you do is you have a huge list of images of people who have suffered injuries and brains that are perfectly fine, and you're trying to identify areas where things that pop out that are indicative of the injury. This was not done in TensorFlow, but it could easily be done in that. And it's something that labs should consider adopting. This is something slightly different, which is in angiograms, where we're trying to identify these structures. We're trying to pick out these structures from all the background and you can see that, again, this wasn't used TensorFlow, but it was a deep learning method that was able to pick them out pretty well. We can see them pretty well. It's a matter of getting the computer to figure them out. Okay, so I've gone through this a little quicker than I expected, but why should you learn TensorFlow? And this is really the bottom line. I've been looking around lately, and when people are asking for your skills, they want to know if you've touched TensorFlow before. There are a lot of companies that are currently using it. Part of it is because of the Google cache. Especially startups seem to have this idea that if they're using Google's product, Google's going to come along and buy them, and they can retire. Learn TensorFlow. If you just put it on your CV, it's going to help you get your foot in the door. And the other thing that surprises me sometimes when I talk to people in the department is a lot of people don't know Python, R or MATLAB or other things. If you're finishing a master's degree or a PhD in this program, you got to know Python. It's at this point it's a requirement if you're hoping to get a job outside of academia. So if you don't know Python, learn it. You might want to talk to Marcus. He might be able to help. That's all I've got. Sorry I went through it all so quickly. Like I said, Kayvon is unfortunately not here today. It's because he doesn't really care about his students that much. He's actually missed the last couple of presentations from his students. He's out of town, but he sent his apologies for not being here. I'd like to thank a lot of the other lab members that have helped and who contributed some of the images that I presented. A lot of people in biomedical engineering gave me some feedback as far as the martial arts project. These are machine vision experts, and I appreciated their help, Bernard Martin especially. And again, thanks to the NSF for paying me. And that's it. That's all I got. Anybody have any questions?
Yeah, go ahead, Marcus. I was just thinking, I have some examples of medical examples of the use of TensorFlow that I could show if you'd like. After you discuss, because you have time, and I have some examples to show if you'd like. I mean, I wasn't planning on it, but I was just looking through some decks that I've got, so I'd be happy to show some medical examples if you want. But go ahead.
Sure. If you want to switch over to
just to kind of get our mind going on what you can do with this thing. Would that be okay, Mitch?
Now, a lot of the examples you showed here were a lot of supervised examples, and they had labeled data.
Use that machine there?
Furthermore, some of the medical imaging, we know that it's kind of like a semi-supervised data set. People that have played around with TensorFlow know that there are these avenues, but what about unsupervised or semi-supervised?
Sure. TensorFlow is pretty flexible. There's a lot of things in there that you could use. One of the biggest problems with deep learning is getting labeled images, especially for medical imaging. You need sometimes millions, at least thousands and thousands would be helpful. There are some libraries out there that can help you train even without having that kind of image.
I know that requires having a physician to put hands on the data.
That's the big problem. I mean, when you have labeled data, you need to have a human to label it, which is, I guess, relatively easy if you're just doing numbers. It's much harder when you're doing something complicated like medical imaging. But I can't think of a specific method in TensorFlow, but I know they do have approaches for unsupervised learning as well.
Now, as a technicality of this, because of deconvolution and TensorFlow, is the output image treated as a anonymized image with respect to biomedical?
That's an important question.
That's a good question. I don't know why it would be, if you're giving it an anonymized data in the first place. Yeah, I'm not sure how to answer.
I guess a good example of this is Dr. Guan's work with the Dream Challenge and the Dream Mammography Challenge. One of the big parts of it were you didn't actually see the real data. You saw what they called anonymized data.
Mm-hmm.
But furthermore, you can, where it is data, there are ways for you to get that output image. And technically speaking, as far as their guidelines were concerned, those were anonymized biomedical images, and therefore could
That'd be really, that's something we could look into. That would be very useful to know. You know, it's one of my, I don't have the answer to this, but one of the things I am interested in is comparing the deep learning methods, Alex, with for image recognition, with the fast Fourier transform methods, because there's a lot of similarities. You know, I mean, basically you're just selecting on different spatial frequencies, and the question, I guess, is when would there be enough spatial frequency, cutoff to satisfy, that field of PHI, which is medically imaging oriented, that there wouldn't be any identifiability. There's probably a literature on it. So it'd be something to look into. So I got this deck from Jeff Dean, who is.
Did you look into Torch at all?
Yeah, I haven't played with it, but I mean,
Torch.
there's other things besides TensorFlow out there, and arguable which is better, which is a lot of it's a matter of choice. The reason I would push TensorFlow is, again, just the Google name. It does carry some weight, but it's not. I mean, there are other alternatives.
Facebook's a pretty big name.
Yeah, I know.
Right.
As much as deep learning is a hot topic these days, one of the further sub-hot topics of that are GANs. Does TensorFlow have the ability to do GANs, or generative adversarial networks?
Yeah, I think so, but I haven't used it.
I know that's one of the main reasons people go to PyTorch.
Right. Yeah, I mean, there was somebody I was listening to a couple of months ago who was talking about some of those advantages in PyTorch. But I would think that at this point.
And then if anyone wants to learn more about PyTorch, which is another library from Facebook, we have an Arbor Deep Learning event coming up on November 18, and we will have a core developer of PyTorch giving a keynote visiting from Facebook AI Research. So he will be talking about advantages of using PyTorch over like TensorFlow and some other libraries.
This is smart. You can buy this all.
Yeah.
I think we got it up on the Midas site too, because we put money into that.
Yeah, it should. It should be email.
Yeah, no, it's really good. There's been a kind of a discussion between this fellow Jeff Dean and my laboratory, and it's been. So I had this DAC, which is useful. I was trying to come up with some kind of discussion for a company in Boston who had asked me to come in and consult with them on Monday. And they're, interested. Everybody wants to know, what do you think about artificial intelligence? So I was just kind of like dragging through. And, frankly, it's something that's coming up, kind of at the health system level. So, some chair sends an email to me, and Dr. Rungun says, well, what do you want to do about artificial intelligence? And it's like, oh, God, that'll ruin your evening. So, and so, I was just collecting up various facts and decks and trying to come up with some kind of story. And there's a TensorFlow piece in this deck. So, I wanted to give the attribution. And we received this into the lab June time frame, so it's a little dated. In the first part of it, deals with, this slide here I had to think about for a long time, actually. And we talked about it in our lab meeting, in fact, just to kind of get through the philosophy of what the difference might be between machine learning, which is a method that you just specialize, the deep learning method might be a specialized version of that, and the artificial intelligence, so that I can figure out how to describe this to, our administrative leaders, and actually it's a pretty good thing to think about, that the artificial intelligence is involved in, trying to get a machine to make machines smarter, as opposed to having the computer learn. And I think that's just kind of to hold that in the back of the mind, I find it to be useful for me in kind of describing these things to people. You know, and obviously people getting more interested in it. I'm sure that curve is wrong. You know, here's your cat. I don't know how dogs lost out. You know, and I thought this, so one little personal story for me was that I was doing a lot of this research myself, not for image recognition, but for image compression, data compression. Back in the 90s, you know, when I was just getting started in my career, I had these neural nets. I was really excited about it, you know. And I got DARPA going on it and so on. And I got a call from the engineering college, and I remember vividly the call, and this professor over there said, "I hear you're working with these neural nets, you know, and you need to stop doing that. They're a black box. You'll never get promoted. It's a disaster. Don't do it." I mean, and I quit. I mean, I was just dropped cold. Obviously, we didn't have the computing power at the time. I probably would have died anyway. But I took the advice, and there's the point about this computing power. And so that's kind of what's happening. And you know, there's your spatial, there's your anonymized cat for your health record, Marcus. So you know, it's got to smear them off a little bit. You know, the question is it of any use? So let's skip through this. And then I was really interested in learning more about it. So I spent some time kind of drilling through and playing with little toy examples and the like on TensorFlow, because you know, and part of it was you know, this, and there's the white paper, which is useful to, you know, I downloaded that. It's really useful to take a look at. But you know, it was kind of this, which is probably a marketing slide, right? But you know, it took off. So I'm glad you're bringing it to our attention, because it's something we need to know about, and I'm sure this Google cache's got a lot to do with it. There's some of the other, there's Torch, for example, so I think that's going to be fun to learn about. I'm going to try to go over to that thing myself. You know, I did get a chance to go onto this page and look around. You probably went in there too.
Well, that's the one thing I'd say. Another reason to go for TensorFlow is that there's so much out there. Anybody
It's amazing. It's nuts. I mean, you know, it's hard to keep up with.
Not just from TensorFlow itself, but from real users. There's tons and tons of blogs, and people are using this all the time.
Yes.
And talking about it.
And so this is really was the point that I wanted to bring to our attention here. You know, I'm a solar power guy, so this is a simple example of just trying to figure out, you know, kind of a look to see how many homes might be good for solar panels on your roof kind of thing. I mean, this is a simple example they gave. But now we're getting into medical, which I thought was fascinating. You know, this was cool because many of us worked on digital pathology for a long time, and I thought this was a really particularly good example because it brings this whole multi-scale. So think about, the idea is that what you'd like to do is ultimately encode and ultimately analyze histological images, which could be virtual images in a pathology lab, to move away from the idea of anatomic pathologists looking through microscopes all day, making calls about, you know, rare cells or something like that. And so what I thought the neat approach here was this, you know, kind of multi-lens, multi-magnification approach that, you know, so you can imagine a new kind of microscope where you're just going all the way from, you know, water immersion or oil high power all the way to low power. So you get your field of view, and then you could put this on a microscope stage and moving around. Next thing you know, you got a big virtual slide. But you know what you have here, which is neat, is that you have the kind of nested inputs of the multi-magnification, which I think is going to lend itself to the you know, to the processing with the layers, you know. And then they show the example of you know, this is not microscope, but this is medical imaging. And you know, the old approach, the first generation was the anatomic pathologist is trained. The second one would be that you would have some kind of simple training set, a lot of false positives, and false negatives as well. And then using this kind of approach, it's a needle in the haystack piece. And one of the things that's advantageous for this is that there have been a lot of like human factors studies that, you you want your biopsy to come into the pathology lab at 2 in the afternoon or 11 o'clock in the morning or something like that, because there is a fatigue factor that happens with the anatomic pathologists doing the readings. There's no fatigue factor, of this thing. And so, and you can see that these numbers are, the American College of Pathology, which is the, a board that oversees the CLIA labs and everything like that. You can't ignore these kind of numbers, and the days of the anatomic pathologist are numbered. The thing that's making the big difference is that it's a company called Inspirata that has worked with Philips to get microscope imaging machines into like anatomic pathology processing centers. And so the FDA stamp of approval would come through the machine and then would reach back into the software. So we're going to see in the next 5 years or so all of this coming into the pathology labs in a big way. Okay, this one here was, I had a chance, it's worthwhile, I can leave the material with you. This is a decent one to look at. This has been, this is next gen. First gen, second gen was, telemedicine, take a picture of the skin, send it to the dermatologist. Well, this is now you have an image library, train it up, send it through this, deep neural network scheme, and read out the stages of the skin cancer. Safe bet. This one I thought was really cool. I hadn't had a chance to show you guys this one. This is actually something that it could be a dream for many of us who are trying to get three-dimensional images of cells, but are troubled by the fact that you have to do the fluorescent labeling, and sometimes when you do multi-labels, you get into problems with the chemistry. One label works, the other label works, you bring them together and you do 2 or 3 labels, they don't work so well together. So here you could get a bright field stack that was unstained and related to the stained images, say from 3D confocal, but then impute the data back to the unstained specimen. So at the end of the day, you don't have to stain them. So you could use like a 3D phase contrast or something like that, and then move labels. So here the nuclear blue, and this is related to Alex's thesis, and it kind of makes you sick to your stomach. I mean, because we were having so much trouble getting these pictures. And these guys are doing, and these are the same kind of experiments we're doing in our own lab for reasons that are methodological development and proving out something. And, these darn Google guys are, and if you look at that, that's like day 14 of we've got an experiment right now where we got day 1, day 2, all the way to day 14. We're looking at controls versus treateds, and we're turning terminally differentiated cells back into stem cells, and then over the terminally differentiated cells and looking at the chromatin and everything inside of it. We're doing all this labeling. It's time consuming, it's expensive. Think of the day if we could have a training set with labels and then go to unstained and then do the mapping, something like that. Now, our area, genomics, big area, lots of varying colors out there. In this one I looked at, I have maybe Alan or some of you experts know about some of these tools. This is one that Manolis Kellis was involved in. We know him pretty well. And Olga Tralinskaya is an old friend. She was Yang Fangguan's mentor. So these people are well known to us, and this is a really pretty good, these are different papers. So the Tralinskaya paper would probably be deep C, would be my guess. The Manolis Kellis paper, I think we know that one pretty well too. So there's a lot. Alex has got a brand new review article that's just about ready for submission, where he's done a deep dive on machine learning and deep learning in our area of pharmacogenomics, and there's a whole table 1 in there, deep learning applications in bioinformatics. The damn thing is 2 pages long, and a lot of those are in here. So this is this variant collar. Now, part of this is really going to be pretty important for us. Why? because Google has made this incredible investment into bioinformatics. They wrapped it all up, they put it into Chrome, and they're sending it out everywhere. And we could pretend to ignore it if we want to, but we probably don't want to ignore it. And so we got to be aware of it. And you know, they've got data. They're winning prizes. They've been I think you know that Verily is an alphabet company associated with Google. So you got the broad capability, the Verily capability, and you know what they're trying to show you is that 98 versus 99. You got to make a decision there too. But these Google tools are taking on the best in class, and it's important to know because they will now. The good news is many of you could go work for them. They pay good, you know. But I think you know the point that I wanted to dive in on with the TensorFlow is that we ignore this at our peril because you know the West Coast is coming in strong on us with brand new capabilities that are going to be part of our workflows for the future. And so you know integration. This is something that I think has been out there for a while, but it's happening. That is, in the old days, you know, think of the next-gen sequencing core and bioinformatics core, two separate places. Well, you know, Illumina and others are going to fix that for you. You know, and I've been spending time down at BCI Shenzhen. It's the same story. You know, the company would like to disintermediate the bioinformatics analysis by bundling the software with the sequencer and selling that as a wrap service offering. You know, because the trend in the sequencing business is called the race to the bottom. So you know, as the price of the genome, you know, approaches $100, say in the next few years, it becomes mass commodity. And so the profit differential on the sequencers are going to be in the analytics and not in the sequencing itself. And so you're going to see these big companies are going to like merge their capabilities tightly in with the sequencers, and they're going to be sold as products together. And that's going to be outputting analytic, you know, already analyzed data into our hands instead of the data that we would analyze. Something to think about. I believe that. Of course, if you disagree with me, I'm happy to disagree because I'm just making this all up. But I think it's true. And then, of course, the bigger thing in healthcare. I just had a very interesting conversation with this guy about an hour and a half ago who was over in Learning Sandeep, who's over at Learning Health Sciences, and he's working with the people over in the medical school, Malakar, you know, the new curriculum guy, Raj, the dean, and Malala Grukar. So anyway, they're trying to figure out what data science should they put into the medical curriculum, and where should they draw the line. And you know, and there's all kinds of things now having to do with there's issues. For example, machine learning tools are coming into, you know, devices and, you know, are putting out output and driving clinical decision support. So the question is, what does the physician and training of the physician have to know about any of this? And, you know, there's going to be a big blur between, you know, as we try to bring in more phenotypic information from, you know, EMR and other sources and link it with the bioinformatics. This is going to be ground zero for the next wave of innovation with, you know, machine learning and data science. Biomedical data science is what I want to call it, right, sitting in the middle of it. So it's an extension of what we do. And of course, this is being driven by the outside because they see that's where the money is. The vendors see that's where the money is, so there's extreme market pressure to develop this kind of stuff right now to answer all kinds of questions having to do with basic stuff that would enhance clinical decision support, like what dose of warfarin should I give this patient? You know, something that you would do in the clinic, or, you know, outside. Like, for example, the guy was telling me that, you know, there's a big problem with high-risk patients being discharged from the hospital only to find their way back and readmitted into the hospital, and that costs a fortune because with the current laws, the hospital, like us, would be liable for that readmittance charge. And so what he told me about was fascinating is there's an algorithm it's called LACE. And it's run on everybody in the hospital in the inpatient setting. They just switched it on. And so they switch on a learning algorithm against all your hospital patients, and it alerts the docs and the nurses and the caregivers in every single room in the hospital who might be readmitted based on risk factors coming from the algorithm.
It's like a health recidivism.
It is. It's exactly what it is, and what they want it. And so they might say, you're on a lot of cardiovascular medication, but we're going to send the pharmacist down and give you these pills because we don't trust that you're going to go to the pharmacy and buy them. And so it's a resource allocation mechanism to prevent this recidivism. You're absolutely right. So everything from very basic all the way out to the border of the hospital and then beyond. Like, for example, in Livingston and Washtenaw County, emergency room utilizers are on a Poisson distribution, and a lot of the emergency room resources are taken up by a small fraction of repeat offenders that keep going back into the emergency room every day of the week for various reasons. So you could run an algorithm against that data, which we have, and machine learning against that, and identify, I don't even know how much machine learning you need, identify all those patients and intervene and try to figure out, send a caseworker out there and try to figure out why they're going back in there and prevent them from doing so. This is the kind of stuff that's happening right now.
Maybe they're losing health care coverage.
Yeah, well, I don't know. So this learning to learn thing is, something to think about in terms of artificial intelligence. Those are just a fraction of the of some of the medical imaging, pathology, radiology, variant collars, bioinformatics, EHR, out into the community. Everywhere you go. I mean, there's one more thing that I think is really worth looking at. Let me see if I can find it. Just to give you a feel, I don't know how many people were tracking this Personalized Medicine World Congress, PMWC, which is coming to Ann Arbor. There's a couple things that are worth knowing. In 2019, we're funding the Machine Learning in Medicine, Artificial Intelligence in Medicine Conference that was in Boston. It's moving to Stanford in 2018. In 2019, we're bringing it to Ann Arbor. That is the #1 conference for machine learning in health, in medical research and healthcare in the country. We're bringing that to Ann Arbor in 2019, August. And we're going to have a workshop at that point. So that'll be good. What I want to show you, what the Personalized Medicine World Congress, they're coming. We're having an event that started in Silicon Valley in San Jose years ago. Many of us go to that. Then Duke decided they wanted a satellite. There was one in Israel. They opened it up in Israel. There's like franchises. So then, it was Stanford was associated with the first one. Then Duke bought into it. Now they're making the rounds to Ann Arbor. We're bringing them here in June. They just sent out a notice on this yesterday, and I counted in the email approximately 200 companies that are involved in machine learning and in artificial intelligence, having to do with, all the way from basic all the way out to quite applied and translational in the community. Companies that are involved in the space. I mean, it's huge. And there's a little diagram. Oh, good. Let me see. And then I'm done. And I didn't plan on doing any of this, but I think maybe it was okay to do.
So while you're looking at that, one thing I should have said, when TensorFlow first came out, there was a lot of buzz about it, GPU use. It's gotten to the point now that you can use it on mobile devices as well. So
that is fantastic. Yeah, look at this, man. This blew me away, and I almost put these tensor processing units. So that was hardware guy. I mean, I love hardware. I mean, this has got to be some kind of like next-gen GPU or something like that. But, you know, I think it's important to know that they are building, thank you, they're building boxes for this. So it's going to go like a bat out of hell, basically.
What kind of concerns are there? I know specifically in the finance, in the world of finance, machine learning is very hamstrung because the security commissions or whatever, they require that the financial institutions are able to explain what is happening with their algorithms to their clients for transparency. How does that translate in biomedical world when
I think
the
this
doctor's
is,
giving some?
I really appreciate you asking this question. It is absolutely the fundamental question to ask. You know, I certainly asked Sarandeep, who came in to meet with me a couple hours ago about this. It's the right question. You know, I think the answer is that we would only go with the supervised learning, and there has to be some way to look and see. It's like yesterday's seminar. You know, what are the feature vectors? How do they relate back to, you know, something in the cell or something in the patient population that I can, like, interpret? I mean, this idea of this full-up, blinded, hidden layer model, where you push a button and out pops up Felix the cat. You know, I don't think it's going to fly in medicine. But that is the discussion that we have to have right now. And there might be, it's easy to kind of come up with answers and do policy guidance and kind of draw lines. But I think in the end of the day, if people are using a tool that are giving you answers, the way we discussed it a couple hours ago is like, if you're getting into a car and you're driving down the street, you know, you can drive down the street and, you know, you don't have to know anything about the car. I mean, you might know that it runs on gas or electricity or something because you might have to plug it in or whatever. But you don't really have to know anything about it. So, you know, so as people get more and more, you know, used to using certain recommendation technologies in their work, they did say something that was pretty interesting. Listen to this for 1 second. So, there was this test where they would take the there was just a standard practice. If you give blood to somebody, you would take a hemoglobin measurement before you gave them blood and after you give them blood. It's standard of care, and it goes into your record. Okay. Well, there's a paper that's just been published that shows that you know, with the hospital recommendation systems, you know, you'll have the phlebotomists and the physicians and the nurses and everybody. And, you know, you take the blood and you do a hemocrit. You know, you send it down to the lab, you get a hemocrit. And then the standard of care is that there's a box that's checked in the EMR, you know, do a lab test. And everybody does a lab test. It's like 100% compliance. Then somebody goes in. This is the experiment. That's the control. The experiment is somebody in the computer room checks off the box. So you've trained these doctors that the best thing to do is do the hemoglobin measurement after you know, do it before and after. You've trained them, and you've got them all doing it, and they're looking at it. And then you go in the back room and you click off a box. What do you think happens? Do the doctors continue to do the hemoglobin measurement after or not? What do you think it looks like? I'll tell you how it looks. It looks like this. They measure it when they are told to measure it. When they're not told to measure it, they don't measure it. And so that's just one example. So you got to think of the healthcare provision in a hospital, say, is a series of recommendations coming from a system. And by and large, what's happening is they're following the recommendations.
We're seeing this change where people went from not trusting algorithms to trusting algorithms.
Yeah, so that's why I'd say that, you know, on one hand, you get in these policy discussions. I had these like high-priced lawyers that were actually working with the Security Exchange Commission and they were trying to like talk to the FDA that says, oh, well, what do you think about that? I was on the phone with these guys a couple months ago. They were asking these questions. You can come up with simplistic answers, but what I'm saying is it's like the automated cars. I mean, at some point you're going to get, like for me, I got this big truck. So if I could push a button and like get it to park this truck, I would be a happy guy. I would let them do it. I mean, I really would. I mean, am I ready to like get rid of the brakes and the steering wheel? I don't think so. But, you know, am I willing to take the first step? Yeah. You know, if it doesn't work, yeah, back off a little bit. But I think as we get more and more into this, we get used to it, we're going to start trusting it more. So my sense is that our understanding of what's actually happening would likely, you know, as consumers of things, is likely going to decrease, no matter what our policy directives might be. So I think it's a very kind of freaky time for us as, you know, earthbound humans who have not had to deal with any of this before. Our job here is to learn enough about it so that we can contribute to its appropriate and ethical uses. All right, that's Mitch. I came in to help. I didn't know, this was not planned, but I hope that some of this additional information gives us an idea and